Lewis electron dot structures are working on it again, and resonance. So you kind of, I don't know if you noticed, but in the quiz you just took, right, there's multiple answers here, depending on where you put a double bond. Hopefully you found that out, that you had to put a double bond somewhere on these questions, and you could have put it in multiple locations. It's this is more complicated than that we're going to be messing with, but this compound is called benzene, and if you drink enough of it, it'll kill you. And what's kind of interesting is if you ever read the label on soda, benzoic acid is a preservative. It's good. It doesn't hurt you, right? Citric acid is vitamin C, and it doesn't hurt you. All this stuff makes flavor. However, when you combine the two under the right conditions, you get a little tiny bit on the part per billion or part per trillion level of benzene. Well, people who drink a lot of soda, now they're starting to drink some benzene, and that's not good. So we did a research project on that. But the idea is the point here is just that benzene is a more stable compound than it should be. It doesn't go away. It stays there. It's very stable, simply because of resonance. You can draw more than one resonance structure. Notice how the double bonds moved. So it's the exact same molecule, it just exists in more than one form. So that makes it really stable. And there's a good number of compounds like that. Like here's another one. Where do you put the double bond? Does it matter? If you move the double bond over to the bottom oxygen, you rotate it. It's the same molecule. You can't even tell. So even though the double bond moves. So this idea is resonance, where you can draw more than one Lewis dot structure just by moving a double bond around. You don't move the atoms at all. All you do is move a double bond around. So, for example, let's take a look at carbonate. Right? Carbonate, Audrey, how many, let's start with this, Audrey. What element do I put in the center of this molecule? Carbon. Yeah, better put carbon in the middle, because that's their general rule, right? Whoever's first. All right, so we don't know shape and stuff yet, so we just throw the rest around there. Okay, then we need to count up the number of valence. Megan, how many valence electrons does all this carbon has? How many? 4. And then I've got 3 oxygens, so 3 times 6. Okay, and then I've got a -2 charge. So Lorena, what's the trick to do that? Add 2, because I've got 2 extra. All right. So 18, 24. Okay. And there's a good habit to prep us for what's coming up. I mean, this semester's almost over. But to prep us for what's coming up, I suggest doing the following. Make octets on everything that's surrounding. Anything left over, you put on the center atom. And that's just really going to help us out as it's coming up. So if you just get into that habit of how you put electrons around, life will be a lot easier. So make octets around everything that's surrounding. And then if there's anything left over, you put it on the center atom. See how I made making octets around them? Right? The bond is 2, so those guys are done. All right. So Alyssa, are there any electrons left over to put on the carbon atom? Each oxygen has 2, 4, 6, 8, and there's 3 oxygens. 3 times 8 is 24. Yeah, so there's nothing left over. But I can't forget, I gotta do my bracket thing. Okay. And Steph, life is going to be more confusing today because we're going to get into some elements that do not like to obey the octet rule. And how you're supposed to know whether it likes to obey the octet rule or not, we'll get into that probably the next class period, because we'll calculate something called formal charge. And what do you want to care? We just calculate this fancy number and we'll be done with it. Right now we're still kind of in wonderland, and we're supposed to just recognize, oh, carbon obeys the octet rule. So Steph, is carbon obeying the octet rule here? No. So if it's not obeying it, we want it to, Ashley, we can make double bonds, but only between what elements? CNOS. Okay. So, Connor, where do you want to make a double bond? Anywhere, right? Now remember the trick to doing this, don't draw the double bond first, please. Erase first, and then draw it, right? Okay. But Paul, is there any reason why we couldn't have made that double bond somewhere else? No, there's no reason whatsoever. So you have to draw how many answers here? Paul, I have a Paul question. Mia, how many structures do you see that we're going to have to draw here? We're going to have to draw 3 of them. And what they want to see in between all 3 answers is this kind of double-sided arrow. You can go like this, you can go like that. It doesn't really matter, just showing that they're being interconverted. So draw the other 2. Move that double bond around to the other 2 oxygens. And there's our answer. So carbonate, it makes it extra stable, because you can have all these 3 different forms. All right, so just keep moving the double bond around, and then you'll have it. Not so bad, right? Okay. And before I send you off on your own, there's just a few more tricks, and this is one of them. Manuel, you recognize this compound? We had I think we named it. Do you remember? Does anyone remember? It's nitric acid. And the only hint I can tell you right now is that it's got a what out front? H. That's the convention. It's kind of nice. So you don't have to memorize acids, right? So if they've got an H out front, that means, oh, it's an acid. But does that mean you make H the center compound? No, because H can only take how many bonds always, Tanya? 1, so you're done. So H can never be in the center. But they put it first. Now, another thing, so that's one thing you got to remember. The other thing you got to remember is these acids, the H is always attached to something really electronegative. So then it can fall off, right? Because whatever's really electronegative sucks up all the electrons, and then that makes that H acidic. So it's not, the H isn't going to be attached to the N. The H has to be attached to the O. So the homework just expects you to know this. So which element, Sydney, would you guess you're supposed to put in the center? Nitrogen. You're supposed to put nitrogen in the center. So you put nitrogen in the center, surrounded by how many oxygens, everybody? 3 of them, and just have H attached to 1 of them. Okay? So if they don't tell you that, then you just have to realize it. All right, something like that. Okay. So that's what makes those acid problems kind of hard, I think. Okay. So Lauren, how many valence electrons do we have to work with here? Just add them up for me, one at a time here. Hydrogen has, nitrogen has, oxygen has. Oxygen has 6. Yeah, so that'd be 3 times 6. Nitrogen has 5. H has 1. Yeah, 1. Okay, so 3 times 6 is 18, plus 5 is 23, plus 1, 24 valence electrons. Okay. Let's see if you can get this thing to work. Again, make octets well, not hydrogen obviously, but try to get everything to have an octet except for that center atom. If you have anything left over, then you put those dots on that center atom, which is the nitrogen. So see if you can distribute those 24 valence electrons in that habitual way. And you know what? Pretend this is an exam question. And they're saying write resonance descriptions. So if they're saying write resonance descriptions, that means you're moving what around, Dylan? You're moving what around? A double bond. And there's only, since I've done this a lot, my eyes just looking at it, I know exactly where these double bonds are going. Does anyone else see it? These two, exactly. These two oxygens is where the double bond's going to be bouncing around, right? Because then it's the exact same molecule. Why not here? Yeah, it's going to be a different molecule then. If it's a double bond, is it longer or shorter? Shorter. It's tougher. It's stronger. It's stiffer. It's hard to vibrate. So yeah, it's going to be a different molecule. So it's only going to be here and here for resonance descriptions. That's where you're going to be moving your double bond around. See if you can figure it out. I think this is the starting point, right? Because all 24 electrons are used up. So doesn't it work out pretty good? Because now nitrogen, the next step would be nitrogen doesn't have its octet. So what do you do, Giselle? Yeah. So you erase the lone pair first, right? Erase the lone pair, make a double bond. Draw the exact same structure again, but move the double bond. So go ahead and draw both of those resonance structures and then see if we agree. Then we'll go to the boards and finish the rest of this stuff. You can always do brackets. But I think brackets are only required when there's a charge. But you can always do brackets. Brackets look nice for resonance. I don't know why. I think the book likes to do brackets for resonance structures. But right, we'll do little brackets, make it look nice and pretty. All right. So that's the whole idea of resonance. Just move a double bond around between identical atoms so that the molecule doesn't really change, right? That you could rotate it and you'd have the exact same molecule again. So we have sulfur trioxide next. So we can go to the boards and start working on all this stuff and we'll call it a day. Let's do sulfur trioxide before we go on to EX2 though. So wrap up this question. Do sulfur trioxide first. There's your spot all for you. Yep. Just got to keep moving it. So once you draw that first sulfur trioxide, and with the word resonance in there, hopefully your eye catches it, and you see, oh dang, I have to draw how many answers? How many resonance structures will there be? There's going to be 3, because there's 3 identical oxygens that you can move it around on. To me, that's the big hint. You should have 3 answers here. Mm-hmm. Mm-hmm.
So do I just connect with F and F or what?
Yeah, X's in the center.
Like this is just really like since this is all 8, do you just see what?
We'll get there. We'll get there. Maybe Connor can tell you. Looks good. Okay. Make sure you draw arrows between your structures, otherwise you'll lose a point, right?
We don't draw a bracket that we want one point.
No, because there's no charge.
Yeah.
Okay. Once you got it, try EX2. So EX2 is a good example of what you're going to see because some of these molecular structures are kind of complicated, so the skeleton's got to be given to you. And again, just by looking at it, you should be able to identify where these resonance structures are going to be bouncing around on. It's a big hint. How many valence electrons did you get for nitromethane? 24? I think I got 24 too. 12, 17. Yeah, I think I got 24 valence electrons too. There's one more though, right?
Yeah. Or just gonna put it on that one.
Yep. Yeah, and the little arrow in between them. So you'd have 24 use up 24 electrons though. But yeah, that's a good idea.
Don't you have to do another one so you can put another bond?
Yeah. Well, yeah, no, this is it. So there'd be one there and one there. You have it. Oh, not here though. Right? See, because that is going to be a different molecule than this. Because now that little bond is shorter. But if you just if you move that, yeah, those two is it.
Okay.
That's it. Just 2, because there's only 2 identical. Because there's only 2 identical oxygens. Right. Because it seems like you could move the double bond in here too, but that'll actually give carbon too many. 2, 4, 6, 8, 10.
Can't do it here because it's a whole different.
Well, That, and if you do it here, look how many electrons carbon would have. 2, 4, 6, 8, 10. They give it too many.
You'd rather do the double bonds with those. So you should only have 2 answers.
How many electrons you get on there? You have to have how many though? So they all have to be on there. So you put it. So remember the general rule: make octets on everything that's surrounding. Anything left over, you put where? On the center atom. But keep them paired up though. No, keep the dots paired up. Okay, try EX3. It looks like everyone has the right answer here. Xenon difluoride. Xenon difluoride. So they're following convention. The first element's in the center. Yep.
When you put the double bonds here, 12. Like it doesn't matter.
Let's see. Hang on. Why do we have a lone pair here? Oh, you have 24. So if we count this up, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 20. You got too many, 26. Yeah, so there you go.
Oh, right,
And
yeah,
plus,
that's right.
and plus, see on nitrogen, you have 2, 4, 6, 8. He's done anyway.
Okay. But you can move like the double bond between
Then
here
you,
and here.
yeah, then you move it over here. So you erase, put these electrons back
Yeah.
over here, and just put those right there.
But so like we wouldn't be able to put the double bond here though because it would
Well,
change.
yeah, I would. 2 reasons. You're right, because if you put it here, and then it's gonna be a different looking molecule.
Well, because up here, remember how we couldn't
And-
put the double bond like where the hydrogen was? You couldn't put the double bond here.
Yeah, well, also it would give it too many electrons. Because there's another rule to worry about, that octet. Because if you put it here, 2,
Yeah.
4, 6, 8, 10, they give carbon too many.
Okay, so this one we have a total of 22.
Yes, you have to have 22 electrons on there. So on this XEF2, follow the general idea. Remember I said, how many total valence? 22 valence electrons. Okay, so the idea is make octets on everything surrounding. Anything left over, put where? Center atom. So that center atom's going to have how many lone pairs? How many lone pairs of electrons? It'll have all. All right, make octets on everything surrounding. How many did I use up? I just used up. How many did I use up? 16, right? I used up 16. So I have how many left? 6, which is 3 pairs. So just put on 3 pairs and kind of keep them paired up. It'll help you for next class period. Yeah. But make it look kind of symmetric as good as you can. Okay. Xenon is not following the octet rule. So, but follow the general idea. The general idea is how you put on electrons, make octets on everything surrounding. Anything left over, center atom. And that'll save your behind every time. Try xenon, what is that? Pentafluoride, cation.
So the lone pairs can only go in the center?
They have to go on that center atom. So you need one more pair of lone.
Yeah.
What's that?
Do all 5 Fs surround?
Yes. Yeah, everything has to be around that center atom. then it's plus. So there you go. Oh, I think if it's plus, where is this? It's anything that's a plus. That means it doesn't have enough electrons. So you don't write plus here. You subtract. Yeah.
So you can do
Yeah.
this.
So hopefully you're coming up with 42 valence electrons for this, right? 8 plus 5 times 7 minus 1. 35, 40, 42 valence electrons. So on xenon pentafluoride, did you end up with any lone pairs on the center atom? Did you guys end up with any lone pairs on the center atom? How many did you end up with? 2? Or 2 electrons, 1 lone pair? Just 1 lone pair? I see everyone getting just 1 lone pair left. Lauren, is that what you came up with? 1 lone pair left? Oh, they all have to go to xenon. Every single one.
Oh, so it doesn't, even though, because it doesn't.
And they're Fs, not Fe.
Oh.
Yeah, so every single one has to be surrounding that xenon. You know what's faster? Is each one has 8. So 1, 2, 3, 4, 5 times 8, 40. There you go. Yeah. So each fluorine will have 8 around it. 8 times 5 is 40. So you're going to be left with 1 lone pair on that xenon. Oh, and don't forget your brackets. Triiodide, anion. Oh, when you do the lone pairs, they like it on, not over a bond.
So.
You just, space it out. Keep them together like that, yeah. And to kind of help you out what's coming up, make them at the corners of a triangle. It'll help you for what's coming up. Just try to spread them out as much as you can. Yeah. That looks good. So on triiodide, I see people drawing 3 lone pairs on that. And when you draw them, try to make them at like the corners of a triangle or something. It'll help you out for what's coming up. Why do you have 3 lone pairs and Megan has 2 lone pairs? Do you guys have 2? Oh, you erased it.
Yeah, I erased it. I was making sure that was right.
Okay. So you should have 2 lone pairs. So the dots on that center atom, just try to spread them out as much as you can. And that'll help you for what's coming up. Wow, no one did double bonds for boron trichloride. So I can't hit anyone on the back of the head. Mia? You didn't? Right? Because you're not supposed to, right? Because you only draw double bonds for CNOS, right? So boron just simply is not obeying the octet rule. Very good. Yep. Exactly right. There's only 24. Beryllium dibromoide. Yeah. Looks good. See? That's all I have. Did you get them? So you got 3 times 7, right? Plus 3. Yeah, 24. And then 8, 8, 8. There's your 24. You can see if there's stuff in your folders. There might be. There should be.